Thank you so much for that introduction and for this invitation to speak about my work. It's always super fun when I can see names of my colleagues and friends in the audience. So, hey, everybody. Okay, so to make the talk a little bit more fun, well, first, actually, I wanted to say a big thank you to my lab. During COVID, I rotated a lot of my acknowledgement slides to the front because I figure I'd rather run out of time showing you data than run out of time before I get to thank the group. So our lab is really integrated team, and obviously sleep circadian research can't really be done without a fairly big team of people supporting the work. So this is the most recent picture of the group. I also want to thank our funding bodies. We've been very, very fortunate, and especially with internal funding from CSU, CU Boulder, and CU Anschutz internal grants that have really helped me as a junior investigator. Okay, but what I was mentioning before is I'm going to try to make this a little bit interactive. So have your phone ready because we're going to do some things. These are just our Twitter handles if you ever wanted to see what we're up to in the lab. Sometimes we post at like 3 in the morning, so we can get a little punchy. But have your phones ready because I have some surveys coming up. And mostly this is for my own entertainment because I'm all by myself and I can't see all your beautiful faces. So this gives me a feeling like we're actually together. Okay, so for the very first quiz, if you want to grab your phone and you go to the website menti.com. So I'll let you start doing that. I'm actually going to do the same because I'm even going to fill out some of my surveys. And what I'm going to do, sorry for the people at home watching that are, watching this after the fact, but you can actually participate too because I have a live survey. So you go to this menti.com and I'm going to do the same. And you type in the number at the top. So it's 79537464. And you can go ahead and let me know who is out there. Let's see. I'm faculty, but I'm also just happy to be here. So I feel like I'm going to submit that one. There I go, zooming in. Just happy to be here on this snowy day in Colorado. Ooh, mostly faculty. Always once in a while somebody shows up and says it's my mom. I don't know if my mom is really here. Ooh, okay, so another friend in the just happy to be there category. So okay, so mostly talking to my faculty colleagues. That's good to know. I think probably like my students, a lot of them have class right now, so hopefully, hey everyone, if you're watching a little bit later. So back to the talk. Back to my share. Boop. Thank you for humoring me there. So now let's get into really why we're here. So why do we sleep? The whole talk is really going to focus on understanding how sleep is really important and critical for human health. And I hope that if you take nothing else away from this talk, that will really be the one thing. So I always show this comic because, well, number one, I read this comic all through grad school, but I'm interested in sleep because of this fact that we spend so much time doing this behavior, which is essentially involuntary, and yet we know very little about its function. We know it's restorative, but we really don't know how it's restorative or really what it's doing. And every subfield within sleep kind of has a different definition of the function of sleep. So what is sleep? Sleep is a definable behavior, and in humans, we can measure it with this EEG right here. This is tracing from an electrical activity that's measured across the scalp using electrodes. These top 4 lines are electrical activity measured across the scalp. These next two lines are eye movement, and this bottom one is chin muscle activity. And so you can see as we transition from wake into stage 1 sleep, which is considered a very light stage of sleep, we have a very distinct change in the electrical activity that you can see here. So we go from having this higher frequency activity to a kind of slower waves over here and very little eye movement. Then from stage 1, we move into stages 2 and 3, 4, which are we now actually combine and call slow wave sleep. But you can see there's very distinct characteristics that define each stage. So stage 2, if you look at any of these top 4 electrode tracings, you can see certain things. In this case, we call this a K complex. And if you look really closely, you can see where my mouse is here, this period of low amplitude, high frequency activity. Again, very little eye movement. When we fall into the deepest stages of sleep, called slow wave sleep, it's really dominated by this high amplitude delta waves, which even are picked up on the eye electrodes down here. And then REM sleep, which actually I'm not showing, but again, is very defined. So the point of all that is to drive home this idea that although we don't know how sleep is doing what it's doing, it's very clearly defined brain state and behavior. And I always like to show those sleep stages just to make that point. Very clear things going on. Your brain is quite active, but we don't know how it's working. We do know that all animals sleep. So really almost all organisms can be observed to have some sleep-like behavior. And in 2017, this paper came out in Current Biology. That was the very first report of an organism without a brain or centralized nervous system showing or demonstrating sleep-like behavior. So this really shows how ancient of a behavior sleep is, because it actually predates the evolution of a centralized brain and nervous system. So not only do all animals sleep, but every tissue in our body, or at least almost every tissue, possesses the core clock machinery that allows it to oscillate. So almost all of these tissues, if you take them out of an organism and let them oscillate in a dish, they will actually oscillate independently, and these activity will cycle even up to days, if not weeks, if you continue to provide substrate. So the central clock is located in the brain, and it can project out and synchronize all of the other clocks in the body. And so if you think about how all those animals and how all these tissues originally evolved, they did so when there was very clear light dark schedules. So when the night sky looked like this, it was totally dark, and in the daytime it was totally light. But of course, we know that's no longer the case. These are some pretty satellite images, but we can see that we now have this ability to manipulate light, to manipulate our environment, and to be active and working at all times of the 24-hour cycle. And that has in part played a role with some changes in average sleep time over the last 50 to 75 years. So across the bottom of this graph are years that some surveys have been taken that included sleep duration reports. And on the y-axis, you can see sleep duration per day in hours. And over this time period, there's been this steady decline, going from about just over 8 hours to just below 7. And so it's really been almost an hour and a half decrease in average sleep time reported. And these particular data are from the US, but this is actually now a worldwide phenomenon, certainly the case in westernized cultures. Okay, next quiz. So this is my funnest quiz of the day because of the recent daylight savings. So my question for you is, how much sleep in hours did you get last night? So here again, we go to Menti. It's 246939119. You're going to be really disappointed in me as a sleep researcher. Okay, so you should have options to submit. 5 to 6, 6 to 7, almost enough. Don't be embarrassed, it's anonymous. No alarm clock, you lucky duck. Feeling good. Oh my gosh, am I gonna be the only one? So I'm the 5 to 6 because I was, instead of sleeping, making these surveys and making sure they worked. Because I recently had a talk where they actually didn't work and it was really sad. Okay, so again, the cool thing is if you're watching this recording and you go do the survey, you will also be able to see the results shift and change in real time. So actually pretty good. Most of you on the call are getting the American Academy of Sleep Medicine's recommended 7 or more hours per night. So I'm gonna give you 6 7s the benefit of the doubt and call that 7. And if you're interested, there have been studies that have really examined how the COVID pandemic actually shifted our sleep schedules in different ways. Okay, so that just gives you an idea. I mean, that's pretty, actually, I would say that's better sleep than most of the responses I typically get from these talks. So as I mentioned in the very beginning, we spend quite a lot of time asleep. Almost a third of our entire life is spent doing this behavior. We do know that total sleep deprivation is fatal. And a lot of that early work was done at the University of Chicago, where rats were subjected to unrelenting sleep deprivation that ultimately resulted in total organ failure and death. It's obviously not a study we can do clinically, but there is actually a clinical diagnosis called fatal familial insomnia, which is a prion disease that results in progressive insomnia and ultimately death. And again, by no one specific mechanism. It's actually, again, it's a total organ failure, but it's highly, highly rare. And again, this function of sleep is unknown. So why do we lose sleep? We know, obviously, based on those things, we know losing sleep is bad, but why do we lose it? Well, behavioral sleep curtailment is the most common form of sleep loss, obviously for different obligations, social reasons, family, work. We also typically think of normal aging being associated with a reduction in both sleep quality and quantity. And so I'm not an aging researcher, but I do, as I've started to become more and more integrated and involved in the center, I like to think of sleep and circadian disruption being potentially an insight into almost like accelerated aging effects, because some of the impacts we see are somewhat comparable. Sleep disorders are another way we lose sleep. For example, insomnia and sleep disordered breathing being two of the most common. Now, until really recently, sleep research really lived in this field of memory, cognition, reaction time. So sleep loss was considered really important determinant of, negative like performance. So for example, not getting enough sleep is associated with a high rate of car crashes, fatal car crashes, medical errors, a lot of early sleep research. And I say early, but that's actually only about 20 to 30 years ago. A lot of research into the effects of sleep loss on reaction time and memory and cognition led to a lot of changes to medical resident hours and on-call limitations, hours limitations, but also these really large world-scale disasters. In the final causal reports, there was some element of operator fatigue that was listed as one of the reasons for these. And then really more recently, have we started to think about sleep loss as a threat to human health? So we know that not getting enough sleep has been associated with some forms of cancer risk, bone loss, and a cardiovascular disease, including stroke. But our lab has focused on this link between sleep loss and the metabolic syndrome. So the rest of my talk will really focus on risks for metabolic syndrome that change and with sleep and circadian manipulations. So if we think about metabolic disease risk, and specifically here, I'm talking about type 2 diabetes risk, we think about three big traditional risk factors. And these are the things that you think about that your primary care physician might ask about, which is, being overweight, family history of diabetes, and physical inactivity. So across the x-axis here are the odds ratios for developing type 2 diabetes given these traditional factors. So now if you watch the title of this slide, it rotates to actually link type 2 diabetes risk and sleep and circadian factors. So now when I overlay these, you can see that all of these sleep and circadian issues. So here, this is sleep apnea, which I mentioned before, with different definitions of sleep apnea, difficulty maintaining sleep. So that would be a type of insomnia, shift work, short sleep duration down here, different assessments of sleep quality and sleep duration. So you can see essentially every single one of these sleep issues are associated with increased odds of developing type 2 diabetes. And most of them are actually associated with bigger odds for for diabetes risk than one of the big players that we think about, which is physical inactivity. So I really always show this slide to make it clear that this is a clinically significant increase in risk when you're not getting enough sleep or potentially sleeping at the wrong time of day. So now, given that background, I'll move into a little bit more of the data in which our lab has been involved. So this is the outline for the rest of the study. I'll show some of our data in humans, some of our data in a dog model. Most of these have been published, but I'll also show you a bit of unpublished data, and then we'll do one final quiz, which will be a choose your own adventure for future directions that you'd like to hear about. Okay, so insufficient sleep in humans. Well, how do we study that? I always love bragging about the lab, and especially love talking about it to fellow RAMs, because the CSU facilities built our lab. They built the sleep and metabolism lab from scratch, based on the design of a couple other sleep labs that are out there. So really taking the best components that were kind of out there and then taking an existing space and retrofitting it to be a really, really top quality sleep lab. So these are just some pictures I always like to show to thank the facilities team and all that they did to get us to where we're at today. So you can see some of the progression. So now we have this as one of our sleep rooms. So you can see we have here a hospital bed. So it gives us the clinical control and abilities. We can, put people in specific postures that we need based on some of our outcomes. We can do muscle biopsies or fat biopsies within this room. But at the same time, we also have a little bit more of a hotel or dorm feel. And this is really important for our lab because people come and live in the lab for a number of days. And most sleep labs are in clinical research centers, which are very much like a hospital room. They are a hospital room, actually. And so there can be some anxiety associated with being in the hospital, but also just, codes are being called over the intercom. There's beeping and lights. And in some cases, we discovered after the fact that the bed had a vibrating tool for anti-bed sores. So I saw that a lot of my Anschutz people are on the call. So that the beds up in the CTRC actually vibrate to prevent bed sores. So that can be a bit of a problem in sleep research. Okay, one final thing to point out here is this little square on the left wall, which looks like a light switch, but is actually a through the wall blood sampling port. So as you'll see in some of our data, we are very interested in how some of our manipulations impact overnight circulating factors. And so to do that without disturbing sleep, we can actually run the IV line through the wall and we can sample from outside the room. So a really big focus of our lab is this idea that, sleep and circadian disruption actually get all the way to the tissue and they impact the tissues. And that makes sense because we know that each tissue, especially these 3 metabolic tissues shown here, possess these core circadian clock components. So in the past and kind of in the past few years, we've really focused on adipose tissue and both at the molecular level, but also kind of the functional output of adipose tissue. So we've looked at a lot of free fatty acids in circulation. But more recently, we've shifted over. We're in the health and exercise department after all. So we've really shifted our focus now to look a little bit at the impact of these disruptors on muscle. So in this ongoing study, we are working with Dr. Ken Wright, who was one of my faculty mentors at CU Boulder, and Dr. Brian Bergman, who is another faculty mentor at Anschutz, to determine the impact of insufficient sleep on muscle tissue. So this study is run by who I call my professional unicorn, Ellen Lyons, as lab manager of the Sleep and Metabolism Lab. And for this study, we recruit healthy, lean men and women. I know this seems like a very small age range. We actually have a very specific cutoff of 35 because of age-related changes in sleep architecture that starts to happen at age 35. I know it's super depressing to me too. We recruit sedentary people because we bring them inpatient for a number of days and we don't want to inadvertently be studying the effect of imposing inactivity on someone. For the study, for data on which I'll show you results, we have 18 people completed. And we put them on a very strict pre-study condition. So before they come and live in the lab, they are on a 9-hour time in bed sleep schedule for 1 week. And this is based on habitual time. So for example, if somebody sleeps from 12 to 9, or at least if they had no alarm clock, that's when they sleep, we do work with them. We put them on that sleep schedule for 1 week prior, and we confirm that they're maintaining that schedule before coming in. And then for 3 days before, we give them a very specially designed energy balanced diet. And that's designed by our co-I, Janine Higgins, with the Metabolic Kitchen down at Anschutz. So this is a study schematic to put visually what I really just said. So this outpatient period of 7 days, we are monitoring activity, sleep. You can see here, ActiWatch, ActivePel. And we also have continuous glucose using a monitor that's placed just under the skin. For the 3 days prior, this is when the outpatient diet begins. And now you can see this is the inpatient period. So participants are admitted in the evening on day 1. They have a 9-hour sleep opportunity, followed by 4 nights of 5 hours of time in bed. And you can see we've aligned the wake time. And we can talk about, if you have a question about that, just remind me at the end. Okay, so when they're inpatient, people are monitored continuously. We have to make sure they're not sleeping at times when they're not supposed to be. So they're physically with one of our staff members during all scheduled wake periods. We did make an attempt to mimic activity of daily life. So they do have supervised walks per day that we take participants on, really again, to try to avoid that sedentary, truly almost bed rest behavior we want to avoid. So now just a little bit of a more zoom in of the inpatient protocol. So you can see here, we give meals indicated by the yellow arrows, and then these intensive testing days are shown on these dotted lines. So we'll zoom in a little bit more there. So these days are identical. So this is the first, it's after the first night. So it's actually day 2 and day 6 here. And so again, I mentioned that we set all of our schedules relative to habitual wake. So this schedule is for someone who might normally wake up at 8 a.m. And the reason we do this is because everybody is so different in their sleep schedule that from a biological standpoint and a circadian standpoint, if you wake up at 6 a.m., your 7 a.m. is going to look very different from someone who typically wakes up at 9 a.m. For them to wake up at, and eat breakfast at 7 a.m., that's going to be considered their biological night. So we align everything to habitual wake time. We take saliva samples when people wake up, and we use that as a measure of the central circadian clock. We conduct a variety of testing. Most of this I won't even show you results from, but we do muscle tissue biopsies. We assess insulin sensitivity with this test here. And at the end of the test, we assess resting metabolic rate. So insulin sensitivity, we found that it was significantly decreased. And this is as expected because these are results that we've seen previously. Now, to put this in context, again, I always want to remind us, of the clinical context here. This is the insulin sensitivity index for a variety of groups at different levels of diabetes risk. So healthy men and women have a high insulin sensitivity index. They're at very low risk for diabetes. And then as you go down here, you can see people at different risk for diabetes with high risk down at the bottom. These groups have low insulin sensitivity index, and this is people with diabetes at the bottom. So when our people come in and they have their first insulin sensitivity test, when they're fully rested, their values fall in this healthy range, exactly where we would expect. Now, when those same exact people get put through our sleep restriction protocol, their insulin sensitivity is significantly reduced and now falls within this range between two groups at known higher risk for diabetes. So really taking a healthy, lean, young individual and acutely making them look pre-diabetic. And again, this is transient, so feel free to ask me about some recovery studies we've done because I won't show you that data here. I mentioned we do the continuous glucose monitoring, so we're really interested in glucose homeostasis. So the really powerful thing about the glucose monitor is it can record wirelessly under the skin for up to 14 days, at least the model we use. And it samples glucose every 15 minutes. So we can get a really nice granular view of things. Again, we're able to align this to habitual wake time. So all of the meals are aligned for these people, regardless of when they woke up. So you can see here in the white line, this is, breakfast response, meal response, dinner, and a snack during habitual sleep. And when these same participants undergo 4 nights of sleep restriction, we can now see pretty big alterations in glucose homeostasis. So not only do we have larger area under the curve, especially in response to this first meal of the day, we see this interesting overcorrection. So almost really wouldn't say this is hypoglycemic, but it's definitely lower than the habitual sleep glucose levels. And, we have some hypotheses about that. For example, hyperinsulinemic compensation, but we don't have insulin data from these nights. So you can see here different levels, and then kind of an interesting overnight reduction in glucose, which again, because we have such frequent sampling, we can see this, and we haven't seen this before in published data. So I always think, if you're watching and you're really interested in looking at overnight glucose control in people with type 1 and type 2 diabetes, what's going on here during insufficient sleep. I also mentioned we're very interested in free fatty acids in circulation and kind of anything that the adipose tissue is doing. So these are free fatty acid levels during normal sleep. And this is a slightly different protocol, but I wanted to include it here as part of the story. But we see an increase in nocturnal free fatty acids just during normal sleep. And this has been previously described in both adults and adolescents, this kind of nocturnal surge. And then during sleep restriction, again, using the similar protocol, we see this significant increase in the late night and early morning values. And again, this is maybe not such a drastic increase, but if you think about it, this is a very short period of time, and kind of what would this look like if this behavior were, carried out for days and weeks and months and years and over a lifetime. So we previously have looked at adipose tissue from biopsies. So I'm not even going to get too into the details here, but really this is just assessing the insulin signaling in adipose tissue from some previous studies. And essentially we find that during sleep restriction, the adipose tissue itself has a reduction in insulin sensitivity. And you can tell that here, basically this right shift in the activation of an insulin signaling molecule in response to increasing insulin doses. So really the takeaway from this is just that we did previously show a number of years ago that sleep loss does actually impact the adipose tissue, the cell itself, the adipocyte. But now, as I mentioned, we're really moving toward muscle and interested in how insufficient sleep impacts this other metabolic tissue. So this is how we take the muscle biopsy. It's taken from the thigh. And we know from a lot of work on this topic that that when lipids are deposited in muscle, so ectopically, they can take different forms. So this is an example of isomers when triacylglycerol is hydrolyzed to different types of diacylglycerol. So instead of tri with the 3 fatty acids attached to a glycerol backbone, you can see different permutations of removal of one of those free fatty acids. So this particular one, this 1,2-DAG, has been associated with impaired insulin sensitivity in other contexts. So in people with a family history of diabetes and in people with obesity and diabetes themselves. And so we, as a very first step, we attempted to look at the level of these diacylglycerols, these 1,2-DAGs in muscle. And the reason for that is because we had seen this increase in lipids in circulation, so the free fatty acids that I just showed you. And so sure enough, these are different sizes, different chain lengths of these particular lipids. And sure enough, we do see a significant elevation in some of these species. So this is like hot off the press and unpublished data that we're following up to understand what this means and if these changes are related to impairments in muscle-specific insulin sensitivity. Okay, I'll take a quick jump to the side to show you some data from a large animal model. And this is from work I did in Los Angeles when I worked at the University of Southern California. But I also like showing it to CSU people because of the strong animal research that goes on the vet side of things. So in this case, we looked at sleep deprivation in a diurnal mammal. And so, as I mentioned, it's the dog model, and this was in collaboration with Richard Bergman out in Los Angeles. And the important thing to note here is that almost all animal research, and I guess you could say all mammal research in sleep deprivation, is in rodents. And this is an important point to make because rodents are nocturnal. And so the dog is a diurnal mammal, which is similar to us. So meaning that they are awake and active during the day and asleep and inactive and fasting overnight. And so this is a very well characterized model of diet-induced obesity. And that's actually Dr. Bergman's specialty and focus. And he has spent decades really learning a great deal about human insulin sensitivity and insulin dynamics using the dog model. So essentially what we were able to do is assess insulin sensitivity in a very almost identical method that we use in humans after normal sleep, one night of total sleep deprivation, and then again after a long period of a high-fat diet. And this is because these animals were participating in these high-fat diet studies as part of ongoing studies with Dr. Bergman. And so I was able to overlay some questions about sleep onto this existing model. So again, here, this insulin sensitivity, so very similar to what I've shown previously, we have a high, healthy insulin sensitivity when dogs are getting normal sleep on a chow or control diet. So that's indicated this NSC in white. When these same animals spend, in this case, 6 months on a high-fat diet, they have a significant reduction in insulin sensitivity. So again, I mentioned it's very well characterized. So this is exactly the degree of impairment you would expect given this time period on a high-fat diet. But now the next bar you'll see is sleep deprivation for a single night when the animals were still on control diet. And you can see here a significant reduction that is not different from 6 months on a high-fat diet. So really quite a drastic and surprising, actually, I was really surprised, the surprising level of comparability between the high-fat diet insulin sensitivity and the one-night sleep deprivation sensitivity. And I was actually pretty depressed about this because I was the one sleep depriving the animals. And again, this is transient and the animals would recover because we are doing this in randomized order. So we know that the animals recovered from this, but just the fact that this was so similar was quite striking. Okay, back to humans. So now on to something which in the sleep circadian field is very different, but can be considered kind of a similar investigation. But we're now really interested in this idea of circadian misalignment. And this is also interesting for us because all of us, just had a little circadian misalignment ourselves with the daylight savings that happened last Sunday night. So how do we define circadian misalignment? We can fairly simply define it as this altered relationship between sleep-wake and associated behaviors. So what this means is if we think about sleep-wake and associated behaviors, this is what we mean. Being awake, we typically consider to be associated with eating and being active in the daylight hours, and then being asleep, fasting, and inactive at night. So it's really any mismatch of these activities. So if you're awake, fasting, and inactive, asleep, fasting, inactive during the day, and then awake and eating at night. Even a slight shift. So even, travel to new time zones or this daylight savings time, we would call that morning circadian misalignment. If you have to wake up early and eat dinner at a time that, or eat breakfast at a time that your body would normally be fasting. So we do know that that shift work is actually associated with a 44% increased risk for type 2 diabetes. This risk increases with nights worked per month, so there appears to be some dose response there. And it's really not a small percentage of the US population. It's actually about 20% of US employees work what's called these non-standard hours. And this is an epidemiological study in nurses looking at the duration of shift work, so kind of history of shift work and the odds ratio for being obese. And you can see here the longer time spent shift working is associated with increased odds ratio for both weight gain and being obese. So to dive into this a little bit more and understand what's going on, I was part of a study that was conducted at Anschutz and led by Andrew McHill, who was doing his PhD with Ken Wright at Boulder at the time. And this is a simulated shift work protocol. So you can see, again, the study protocol graph up at the top, and participants come into the lab. They have 2 nights of habitual sleep, and then they enter into what's called the slam shift protocol. And this would be typical for a night shift worker who, after a normal day shift, would attempt the next day to get an afternoon nap before doing an overnight shift. For the next 2 to 3 nights, that includes daytime sleep. So for the data presentation, I'll call day 2 alignment and day 4 misalignment. And you can see here with the red dotted line, blood samples were taken every 2 hours. So this is a highly controlled, this actually is a bed rest study. So you can think about, the impact of physical activity or a lack thereof here as well. So you can see participants were in the hospital bed for the entire study. The temperature and light were kept constant the entire duration of the study, and controlled food intake was given across the protocol. Again, these studies were done in healthy, lean individuals, put on a pre-study condition for 1 week. Again, with the 3-day outpatient diet provided. In this case, they were recruited to be sedentary, but also exercise is always prescribed in our studies 3 days prior. And participants will always do a urine toxicology and breathalyzer test when they come into the lab. I should also note that participants are required to have lived at Denver altitude for a certain period of time, depending on the study. In this case, I believe they lived in Denver altitude for a year. So again, now this is glucose. Across the bottom is hours since awake. So you can see in the white line, this is day 2 alignment. And just as a reminder, this is blood glucose now, not interstitial, like I showed previously. And the yellow arrows indicate meals. When participants are misaligned, you can see now that glucose excursions are much higher, the area under the curve is higher. And again, we have that interesting reduction in glucose levels when people are asleep. They're daytime sleeping in this case in the red line. Of course, I'm always going to be interested in free fatty acids, so we assess that in this study as well. You can see here in the white line, the alignment condition, free fatty acids are suppressed by meals, so you can see them going down in response to meals. But then in the misalignment condition, we again have higher levels of free fatty acids when people are awake and eating during the biological night. So some of the follow-up studies that we're looking at with this is actually manipulating the timing of eating and kind of digging into some of the mechanisms that could be driving both this increase in free fatty acids, but also the impairment in insulin sensitivity. So this is really the end of the data I wanted to show you. And now we'll do our final quiz, which is in our final 10 minutes or so. I'll do a little choose your own adventure to get into some of our future directions and ongoing studies. And then I'll conclude depending on what you choose. So some thoughts, and questions I get at the end of talks have often focused on these countermeasures. So, a lot of people will ask, well, what if I exercise during sleep. And that's always the early morning runner. That's always the early morning runner, especially at ACSM. They're asking for themselves, if they get up early to run, is that going to mitigate some of the detrimental effects? Also, what about if you're not getting enough sleep? Could you get more sleep? That's a study we're following up. And I mentioned this change timing of behaviors. So final Menti, let's go to our phones. And I will reserve executive decision making, because if you pick one of the ones that take too long, I'll probably pick a shorter one. Okay, choose your own adventure, share. Okay, so menti.com, you can see the code at the top, 813093. Okay. Oh my gosh, I accidentally made this force you to rate them. Let's see, I'm just going to submit. You don't have to rate them all. I just figured out. So you can just pick your first choice and click submit. So I'll watch, and after a few people have voted, yes, why am I like this, and other existential questions. That's really what I would love to hem and haw about for the next 10 minutes. But Josie, what does it all mean? What if I wake up early to exercise? Oh, cool. That, I have to say, is not that common of one picked. And I think it's because you're CSU buddies that are asking that. So I'm happy to talk about that, because I don't often do. So choose our own adventure. See, I've programmed in a little wormhole, so I have to picture the right one. Exercise. Okay. Oh, yay. I bet Ed voted because he's on the call. Hey, Ed. Okay, so this study was done in collaboration with Dr. Wright at CU Boulder and Dr. Ed Melanson at CU Anschutz. And it's to get at this question of, what if I wake up early to exercise, or if I somehow give up sleep to exercise? So I get the question actually so much over the last few years. So I thought, well, let's just take a look. So for this study, we recruited 22 healthy, lean individuals. Again, historically, our focus has been in this really healthy age group, but we're kind of moving away to do some more field work now. But again, these pre-study conditions really make sure we're studying our own variables, rather than people coming into the lab sleep deprived, energy balanced diet. And so now what we did was we had two groups of people. We actually had sedentary people. So of those 22, 11 were sedentary and 11 were already active. And so we had them come into the lab, again, a very similar protocol. They spent one night after this week of habitual time in bed, one night in the lab, followed by this glucose tolerance test, and then 3 additional nights with insufficient sleep. We repeated that same glucose tolerance test, and then recovery sleep was provided. So the left protocol is showing the sedentary group, and the right side is going to be the active group. So the active group did the exact same thing. They were previously active regularly, and they continued and maintained their daily exercise in the lab. And obviously we could have done this in a lot of different ways. We could have actually taken sedentary people and both sleep restricted them and implemented an exercise program. But after a lot of discussion with the co-investigators, we thought there were probably too many variables that would be changing by implementing a new exercise paradigm. So instead, we asked whether people who routinely exercise would be protected from the effects of sleep loss on glucose tolerance anyway. So PA refers to physically active, and sedentary, obviously the SAD group. So insulin sensitivity as measured by this oral glucose tolerance test, you can see is significantly reduced in the sedentary group. This is actually nicely in line with and very consistent with previous reports. The physically active group was still significantly impaired, but to a lesser degree, and that lesser degree, there was a trend for there to be a difference. So statistically speaking, they were not protected, but there was a trend. So we probably potentially have a power issue there. So if we add more subjects to the study, we might see that, yes, indeed, although the physically active people are impaired, they are protected by exercising, or at least maintaining their exercise during sleep less. So I'll show you a little bit more of the variables because it's pretty cool, and this is unpublished data. So sedentary group will always be on the left, and you can see here, this is the glucose, blood glucose levels in response to the oral glucose drink, which is consumed at time 0, and insulin levels at the bottom during habitual sleep. Now, if we put overlay insufficient sleep in the dotted line, you can see the exact same glucose drink leads to higher glucose levels throughout the test and higher insulin as well. So probably some hyperinsulinemia attempting to bring down this glucose, but it's really not sufficient. The exercising group, you can already see some interesting differences just in the glucose dynamics as far as how quickly the glucose is cleared from the system. So you can see there in habitual sleep. Insufficient sleep still leads to an elevation in glucose, but you can actually see no change in insulin there at the bottom. Another interesting thing we looked at was whether sleep restriction shifts the central circadian clock. So to do that, I mentioned we do the saliva sampling in the morning as a readout of the circadian clock. And from those saliva samples, we assay melatonin because it's an output of the central clock. And you can see here, melatonin levels, which are high at night, and they decrease in the morning. And this is in dim light. So these are decreasing not because of light exposure. And this is during habitual sleep. During insufficient sleep, and this little caret indicates a phase marker, essentially a readout of the circadian clock. So we identify this as a dim light melatonin offset, which is the time at which the melatonin drops below a set value. And when we're looking at saliva melatonin, we choose 3 picograms per ml. So you can see if you take this line across to the y-axis, this is about at 3 picograms per ml, and this is the time that the melatonin crosses below that. During insufficient sleep, you can now see this right shift in the line. And if we look at the dim light melatonin offset, so again, the time at which the melatonin drops below that 3 picograms per ml, it's much shifted. So just insufficient sleep alone leads to this circadian phase delay of the central circadian clock, almost by 2 hours. And that's just 3 nights. So if you think about this idea of social jet lag, and kind of sleep deprived, staying up late on the weekends and sleeping in, you're essentially inducing this repeated circadian misalignment weekly if you do that, chronically. Anyway, so we're actually in the process now of determining whether exercise actually limits this shift in the circadian clock. And I can hint to you that we think that it does. So we're still in the process of doing those analyses. So with that, I want to leave, at least, 5 to 8 minutes for questions. So I'll go to our conclusion. So I really hope that I've at least convinced you in this talk that sleep and circadian disruption impair glucose and fatty acid metabolism. And I showed, in the animal data, this may be as bad as a poor diet, and not just a short-term poor diet, but really 6 months on a high-fat diet. Even exercise isn't powerful enough to protect us. So I know you early morning exercisers are happy with those results, but remember, the impairment is still there. And exercise is the most insulin sensitizing thing we can do. It's better at insulin sensitizing than diabetic medication, and it's still not powerful enough to beat sleep loss. I didn't show you these in the Choose Your Own Adventure part of it, but we have some hints that optimizing sleep duration can improve metabolic homeostasis in people who don't get enough sleep and who can extend. That's kind of the big question, is can people extend? And circadian timing of behaviors, hopefully we can manipulate some of them to also benefit homeostasis, especially in shift workers.